This video covers the second handout dealing with sequences. On this handout, we're going to talk about convergent and divergent sequences. So first, let's define what we're talking about. If we're talking about a convergent sequence, then we're talking about a sequence in terms of a sub n. Let's say a sub n is 1 over n, right? So then a1 is 1, a2 is a half, a3 is a third, and so on, okay? So if something is convergent, what we're saying is that the limit of the terms, a sub n, as n goes to infinity, is equal to some numerical limit L, okay? In this case, as n goes to infinity, you can see that these fractions are approaching 0, okay? They're getting smaller and smaller and smaller, and will eventually be indistinguishable from 0. So this is a convergent sequence, and the limit of the sequence is 0. Okay, if a sequence is not convergent, it is divergent. Okay, and there's a couple different ways that it can be divergent. You can have some of these sequences, especially if they're alternating sequences, they can tend to bounce back and forth between two different values, and so we don't have a single limit. What else? Something that goes to infinity is considered to be divergent. In some cases, we just say the limit is infinity, but infinity is not a numerical value. So that is a divergent sequence, but it diverges in a particular way, and we could say that the limit goes to infinity, but that's not a convergent sequence still. Okay, let's see here. So a lot of this is going to be based on the concepts of limits. So let's go back and review a few ideas about limits that we talked about back in the fall. I just talked about one of them here, right? If you take the limit as n goes to infinity for 1 over n, that equals 0. Okay? As that denominator becomes infinitely large, the value of the fraction itself will become indistinguishable from 0. Let's see, what else? And then we had these scenarios where we had a ratio of polynomial functions. Okay? So let's say we've got this expression, limit of f of x over g of x as x goes to infinity. So this will be, let's see, it will be equal to 0 if the degree of g of x is greater than the degree of f of x. Let's see, what else? It will go to infinity and be divergent if the degree of f of x is greater than the degree of g of x. And if the degree of these two polynomials are equal to each other, then the limit is the ratio of the coefficients. So let's give 3 concrete examples for these. Okay. So first off, let's see if we take the limit of x squared plus 2x plus 7 over x cubed minus 5x squared plus 2. Okay? Now, remember that as x goes to infinity, everything except for the highest powers of the variable really becomes meaningless as the value of x becomes infinitely large. So all we're interested in is the highest exponent or the highest power of the variable here. So in the numerator, we've got an x squared. In the denominator, we've got an x cubed. The degree of the denominator is higher, and so this limit will be equal to 0. Okay. What if we take the limit as x goes to infinity for let's keep the numerator the same, and the denominator, we'll call it x minus 3. So now the degree in the numerator is higher. This is an x squared, this is an x, and so this will be divergent, and we can say that its limit goes to infinity. In the last example here, let's see, I'll keep the numerator the same. And then in the denominator, I'll have 5x squared minus x plus 1. So here the powers of the x's, or the degree of the polynomials, is the same. And so our limit here is the ratio of the coefficients 1x squared to 5x squared. Okay, so those are some fundamental ideas of limits, and those will go a long way towards helping us solve some of these problems. Also remember, plugging in numbers is helpful, but it is good to think about some of these concepts as well. Right? All right, so let's start looking at the problems. On the even problems, number 2, we get a sub n is n to the third power over n to the third power plus 1. So if we're interested in the limit of a sub n as n goes to infinity, notice the powers of the variable are the same in the numerator and denominator, so therefore the limit will be the ratio of the coefficients, 1 on the top, 1 on the bottom. Okay, let's look at number 4 here. A sub n is n to the third power over n plus 1. So here, the degree of the polynomial on top is higher than the degree of the polynomial on the bottom. That is going to make this limit go to infinity, and this is divergent. Okay, let's see here. Problem 6, we've got a sub n is equal to 3 to the n plus 2 over 5 to the n power. Okay, so in this scenario, now this goes back to a concept I've thought about for many years. When I was a little kid, back in the 70s, I got a calculator, a 4-function calculator, add, subtract, multiply, and divide, when I was about 7 years old or so. And I used to multiply 1/2 by itself over and over and over again, and then eventually the calculator would just say 0. Okay? And that's essentially what's happening here. This is very closely related to 3/5 to the n power. Now you can start plugging some numbers in here. So how is it related to 3/5 to the n power explicitly? If you take this 3 squared off of there, right, let's see, if we call this 3 to the n plus 2 over 5 to the n, this is 3 squared times 3 to the n over 5 to the n. So all we really have to do is put a 9 out in front of that, and so this is 9 times 3/5 to the n power. So when you take a number that's smaller than 1, like I was talking about just a minute ago, when you take a number that's smaller than 1 and start raising it to powers, it's getting smaller and smaller and smaller. Every time you multiply it by itself, the answer is going to be smaller than what you started with. And so this piece is eventually going to go down to 0, and so our limit here of a sub n as n goes to infinity will be 0. So this is convergent. All right, let's see here. What else? Problem 8. Here we've got a sub n is square root n plus 1 over 9n plus 1. Okay, so let's ignore the square root for the moment, right? Let's just focus on this n plus 1 over 9n plus 1 and think about what is the limit for this piece as n goes to infinity. So this is, again, this is one of those examples where we want to look at the powers of the variable in the numerator and denominator. Here, it's the same power. It's n to the first on top, n to the first on the bottom. So the limit for this piece is going to be the ratio of those coefficients, 1 over 9. So if this piece is going to 1 over 9, then the square root of that should go to 1/3. And so our limit for a sub n as n goes to infinity will be 1/3, and this is a convergent sequence. All right, let's see. Problem 10. Problem 10 has some similarities to problem 8, not in the sequence itself, but in the approach that we take to figuring out the limit here. Okay, so notice that again, we've got this ratio of, if you want to think of this as polynomials, that's fine, but you've got this ratio of expressions, and so what we want to do is look at those exponents, right? So let's pull that out and look at it separately, okay? And that's really what you want to do when you're looking at a limit for something like this, is where are the n's and what are they doing, okay? So let's pull out the piece that has the n's in it. The limit here, again, these are the same powers of the variable, n to the first and n to the first, and so the limit is the ratio of the coefficients, 2 over 1. So that says that this piece is going to go to 2, which means that the limit for this sequence should be e squared. All right, number 12. Number 12 is an alternating sequence. We've got this -1 to the n plus 1, and then n over n plus square root n. Okay, so ignore the -1 for the moment, and let's look at what these n's are doing right here. This is the same thing, all right? It's this ratio of expressions involving the variable. They have the highest power is the same. Remember, we ignore the smaller powers of the variable, so we're really just interested in the n here and the n here. So if we look at the limit of this piece as n goes to infinity, that's going to be 1. But now let's bring this back into the picture here. This -1 to the n plus 1, it's going to bounce back and forth between +1 and -1. Okay? And so as a result, it will never settle down to be one of those values and not the other. So this is divergent. The only place where one of these alternating sequences won't be divergent is if it's approaching 0. So let's kind of step back for a minute and talk about this a little bit more. Let's see here. Let me get some values for this. Okay, so I've entered this in the calculator. I can go in the table now and pick out some of these values for what these sequence terms will look like. All right, so if we make a little graph here, let's see, we'll put 1 here, -1 here, and so as the sequence terms go, you'll have 0.5 and -0.58. 0.63, -0.66. And what's going to happen is that the positive ones are going to approach +1, and the negative ones are going to approach, the positive values approach +1, the negative values approach -1. There we go. Okay? So that's what's going on with this one. That's why it's divergent. These will never settle down. They're going to get closer and closer to their respective limits, but there's no single limit for this expression. Okay, So there's that one. Now let's look at a situation where we get an alternating sequence that is convergent. And I'm just going to use a simple one. Okay, so we'll make a little picture here again. And we'll use an example of -1 to the n plus 1 over n. So this is very closely related to that one that I was talking about a few minutes ago, or that I started out with, of just 1 over n. Okay, so remember that this thing is going to 0 as that denominator gets bigger and bigger. It's getting closer and closer to 0. So the limit for this thing is 0. Now in this one, let's see here. If n is 1, this will be positive, and we'll have positive a half. And then if n is 2, it'll be negative a third. And then positive a fourth, negative a fifth, and so on and so on. So notice how it's approaching, it is approaching 0. So we could say the limit for this sequence as n goes to infinity is also 0. The fact that it's coming both from above and below doesn't really make that much of a difference, because if you remember the definition of a limit involves, you know, that epsilon distance and getting it to close in on that. Okay? And so whether it's above or below the 0 line doesn't make any difference. Okay. Let's see here. Let's look at a couple more of these problems. Problem 14 is kind of interesting. We get into one of these trig functions. A sub n is the cosine of 2 over n. So again, just like we were doing with those other problems, pull out the piece that has the n in it, and let's look at the limit for that. Okay? It's the same as the limit for 1 over n as n goes to infinity. This is going to go to 0. So our limit for this thing, as n goes to infinity, is essentially going to be the cosine of 0, which is equal to 1. All right, let's see. Problem 16. What do we have? A sub n is ln of n over ln of 2n. All right, so what's going to happen here? Well, it seems like these are going to, it looks like this one should be bigger, doesn't it? Okay. That's not the case. Well, it will be a larger number, okay? But I mean, it's similar. It has some similarities to those. Let's see. If we take the limit of x squared, let's say 3x squared. Okay, as x goes to infinity. So yes, technically 3x squared is larger than x squared, but as x gets infinitely large, that becomes less and less important. So rather than going to 0, this will approach 1/3. Okay. Another example that we just saw a minute ago is if you have x over x plus square root x. Yeah, the denominator is bigger, okay, but rather than driving this thing to 0, this becomes less and less important, and the limit here is 1. Okay, so what does that have to do with this? Well, if you remember your properties of logarithms, this log of 2n can be split into ln2 plus ln n. So that's what the relationship is between this thing and this thing. Right? These will always be the same. ln2 is not going to change. It's going to be some concrete value, some constant value. So as these are getting infinitely large, this becomes less and less important. And so this thing is actually approaching 1. Okay, so the limit as n goes to infinity for a sub n is 1, and this is convergent. All right, so that's number 16. Problem 18. Let's a sub n is 3 to the n over 3 to the n plus 4 to the n. All right, let's see here. Not sure there's a whole lot that we can do to play around with this. It, again, has some similarities to this scenario over here, okay? In that these 3 to the n's, yeah, they're important, but notice that this 4 to the n is larger, okay? So as these 3 to the n's are growing, this one is going to be growing much, much faster. Okay, and so what we should see is that this thing should approach 0 because this is just going to overwhelm everything else in the problem. And so our limit here, as n goes to infinity, put the limit of what we're taking the limit of is the term a sub n. That should go to 0. All right, so there's a reasoning based approach. Let's do some algebra to this, or some arithmetic operations to this thing, and then hopefully we can see that this is correct. Because the basis for those conclusions that we were making, where you've got like x squared over x to the 5th, is that you can divide everything through by the x squared, okay? And this will be 1, and this will be x cubed, and now it's obvious that this thing is going to go to 0. Okay, so let's do the same thing over here. Let's divide everything, or let's set it up correctly here. We're going to multiply by 1 over 3 to the n over 1 over 3 to the n. So what's that going to give us? On the top, that gives us, let's see here, that gives us 3 to the n over 3 to the n. Here it gets distributed, okay? So, what does this give us is 1, 1 plus, and then this will be 4/3 to the n power. All right? So now this becomes really kind of straightforward to find the limit for this expression as n approaches infinity, right? So just the same way that when you take a fraction and raise it to infinitely large powers, it goes down to 0. If you take a number greater than 1 and raise it to infinitely large powers, it goes to infinity. So we've got a denominator here that's going to infinity, and so our limit here should be 0. Okay? All right. Let's look at, how many more do we have here? Just 1 or 2 more. All right. So problem 20, again, we've got these logarithms here. Let's see here. A sub n is natural log n plus 1 minus natural log of n. All right. So let's see here. So again, by reasoning, what we can say is that as n becomes infinitely large, the difference between n and n plus 1 is going to essentially disappear. Okay? And so the natural logs of these two quantities are going to be indistinguishable from each other, and so our limit here of a sub n as n goes to infinity, in this case, will also be 0. Okay? So there's a reasoning-based approach for this limit. Let's do a little bit of manipulation so we can demonstrate that that's true. Okay? And again, this uses the properties of logarithms, right? Is that if we have a difference of logs, we can restate that as the logarithm of the quotient. Okay, now we've got this piece inside here that we know that the limit of that thing as n goes to infinity is going to be 1. So therefore, the limit of a sub n as n goes to infinity is going to be ln1, which is equal to 0. All right, let's look at problem 22 here. Problem 22, a sub n is the nth root of 2 to the 1 plus 3n. Okay, and again, being familiar with the properties of algebra, is very helpful in doing this problem. I'm not sure how I would have approached this problem if I hadn't rewritten it as 2 to the 1 plus 3n over n. Remember that when you have something written to a fractional exponent, the p is the power, the r is the root. Okay? And so the nth root of 2 to the 1 plus 3n could be rewritten as 2 to the 1 plus 3n over n. And now it's just this, it's the same process that we've seen before, right, where we pull out the piece that has the n's and look at what the limit should be here, right? Again, it's the same exponents for those variables, so therefore the limit is the ratio of the coefficients, 3 to 1. And so this should approach 2 to the third power. The limit of a sub n is 2 to the third power, which is equal to 8. Okay, well, that's it for this handout. We'll have a quiz that goes along with this, and then I've got a second handout that talks about some of the same ideas. So I will get this posted along with its quiz, and then get the next video and next quiz ready, and then that will take us through next Wednesday.